Okay, so now we're going to dig into some trig integrals where there's just trig functions, when there's not going to be multiplying it by an x or an x squared. So first off, I'm going to talk about type 1. And again, these are just my types to try to categorize things. This is when the type 1 is when you're going to use these half angle formulas. So it is necessary for you to recognize, oh yes, I can use cosine squared, which is 1/2 1 plus cosine of 2x, or sine squared, which is equal to 1/2 1 minus cosine of 2x. So again, we only want to use this if it's exactly cosine squared, and I'm going to give you some other examples down here. So if it's cosine squared, you know it's really, really wrong to say, oh, I'll just add 1 to the exponent, right? So this is really, really bad. Don't do that. You can't just add 1 to the exponent. When is it that you can just add 1 to the exponent? It's only when you have x squared. That's when it's x cubed over 3. So if there's something inside, like a trig function, you'd have to do a u substitution. There's no u substitution that will work. That's where these half angle formulas come to the rescue. So it is necessary for you to recognize, oh yes, it's time to use my half angle formula. So this is something you're going to want to have on a piece of paper or memorized beside you at all times, and recognize this is the time to use it. So you take this out and you substitute this in. And I'm going to suggest that you just take the time to pull the number 1/2 outside. And so then you can take the antiderivative of the 1, which is x, and take the antiderivative of the cosine of 2x, La Jolla theorem, so you get a 1/2 sine of 2x. Aren't you glad you know the La Jolla theorem? Otherwise, you'd have to go do a u substitution, right? Okay, let's do this one. So sine squared of 3 theta, and I'm going to be changing letters on you because I want you to get comfortable with it. Okay, so the angle has changed, but we can adapt, right? So I've got to replace the x with 3 theta. So I put 3 theta in here. So this identity becomes 1/2 1 minus cosine of 6 theta, correct? I'm substituting in 3 theta right there for the x. So that's how I get 6 theta. So then I can take the 1/2 on the outside, take the antiderivative of 1. Be really careful. We're in theta land, so do not put an x here. That would be really, really wrong. So when you're taking the antiderivative with respect to theta, you get a theta here, and then La Jolla theorem from this, so I get to here. So be careful what letter you're taking the antiderivative with respect to when you have the number 1 or any number. Okay, so notice both of these have even powers. So when they're both even powers on sines and cosines, you use the half angle formula for both of them. And then you get to multiply it out. Oh gosh, lots of work. And then, oh no, use it again. Okay, let's just walk through it. So sine squared of x will be 1/2 1 minus cosine of 2x. Cosine squared of x will be 1/2 1 plus cosine of 2x. I'm always going to suggest you pull numbers on the outside. So I'm going to pull those two 1/2s outside to make a 1/4. And then I have these multiplied together. I'm going to suggest you multiply it out, right? 1 outside insides cancel. So I get minus cosine squared of 2x. So we know this identity, right? Cosine, so cosine squared of theta plus sine squared of theta is 1, correct? As long as the angle is the same, and this angle is the same of 2 x's, right? So then I can replace 1 minus cosine squared of 2x with sine squared of 2x, right? So sine squared of 2x, sine squared of 2x is 1 minus cosine squared of 2x, right? So take this out, substitute this in. These identities are key. Then I look at this and I think, how do I take the antiderivative of sine squared? Oh, half angle formula. So I do it again. And so sine squared of 2x means I double the angle. So I have 1/2 1 minus cosine of 4x, right? Make sure you know what I'm talking about, right? I'm using this, and I'm replacing x with 2x. So then I get 4x, and finally I'm going to pull this 1/4 outside to be a 1/8. Take the antiderivative of 1, that's x. Antiderivative of cosine of 4x, I get 1/4 sine of 4x. Okay, so then what if I have cosine to the 4th power? So even powers only. So you want to think of that as cosine squared squared, or multiplying them both together. So here is cosine squared of t, cosine squared of t. Get used to playing with different letters because it's going to be necessary as we move forward. Pull the 1/2s out in the front, so be 1/4. If I multiply this out, good old foiling, right? I get 1 plus 2 of these things plus cosine squared of 2t. I can take the antiderivative of 1 with respect to t and get a t. Careful, right? Antiderivative of 1 dt is a t. Antiderivative of this, I'd carry the 2 along, but when I would take the antiderivative of this, I would get a 1/2 from La Jolla theorem. So the 2's cancel, so I get sine of 2t. And then this, I have to stop and think, oh, right, this needs half angle. So I made sure that I put this 1/4 here in the front so I didn't lose it. And then I paused. Okay, now it's time to replace this with the half angle formula. These I just carried along, carried the 1/4 along, replace this with the half angle, 1/2, 1 plus cosine of double the angle, 4t. Finally, put this 4 and this 2 together to be a 1/8. Antiderivative of this 1 is t. Antiderivative of cosine of 4t is 1/4 sine of 4t. Whew. All right, so I want to make a closing comment here. So when we move on to odd powers, so when we have any kind of odd power, so an odd power of sine by itself or cosine, or if we have a combination of even and odd powers, we never, ever use the half angle formula, ever. So the only time we use this half angle formula, let's go back up to the top, is when there's even powers only even powers. It could be 1 even power, it could be 2 even powers, it could be 4th power, but that's the only time this half angle formula comes in. All right, so we'll study other types, but make sure that these are very familiar. These top 2 for sure. This one isn't used as much, but you need to know these identities.